Note that this says that the notes in this section must be used in conjunction with the book because I'm going to refer to things in there frequently. Extrema on an interval. Now we already know that derivatives can tell us if a function is increasing or decreasing on an interval. They can also tell us where a function has a minimum or a maximum value. So first of all, we need some vocabulary. The definition of extrema is let f be defined on an interval I containing some c. So f of c is the minimum of f on the interval if f of c is less than or equal to f of x for all x in the interval. In other words, the y value at c is less than or equal to all other y values of the function in that interval. F of c is the maximum of f on the interval if f of c is greater than or equal to f of x for all x's in your interval. Now, let's talk about what we mean by some words here. Value is the maximum or minimum y value on your function. When we use the word value, it's intending for it to be the y value. C is the x coordinate where the maximum or minimum occurs. We don't usually say the x value. So the word value in mathematics usually refers to the y value. Now, minimum and maximum values are also called the extreme values, or extrema, which is extreme values, of the function on the interval. They can also be called the absolute minimums or the absolute maximums of the interval if we check the endpoints. We must check the endpoints for absolute minimums and absolute maximums. So you had one existence theorem, that was the intermediate value theorem. So if you recall, the intermediate value theorem was your first existence theorem, and it said if a function is continuous on the closed interval a to b, and k is some number between f at a and f at b, then there is at least one number c in that closed interval a to b such that the y value at c is that k. So this is your second existence theorem. The extreme value theorem says if f is continuous on the closed interval a to b, then f has both a minimum and a maximum on the interval. Again, like the intermediate value theorem, it is an existence theorem. It says it exists. Please note, if the interval is not closed, it is possible for the function not to have a minimum or a maximum. And then it says, see the graphs on page 164. So here we have a continuous function on the closed interval from -1 to 2, and you can see that we have a minimum value, which is 1. It happens when x is 0. And we have a maximum value, which is 5, what happens when x is 2. This function is continuous, but it is not closed. So this is not a maximum because we never actually get to 5. We get very close to it, but we never actually get there. We do have a minimum. And here is a function that is not continuous on our closed interval. So we have a maximum, but we do not have a minimum. These comments here refer to those three graphs. So now we're going to find the value of the derivative of the relative extrema. So relative extrema happen where the first derivative is 0. They might also be where the first derivative is undefined, and there's more on that coming up. So here's our function. F of x equals 9 times x squared minus 3 over x cubed, and we want to know what's happening at 3, 2. So first of all, I would consider this function to be written like that so that we can take the derivative. Notice that this is a constant times this quotient, so the derivative is going to be a quotient rule, okay? Low d high minus high d low over low low. When we multiply these, I get 2x to the fourth minus 3x to the fourth plus 9x squared all over x to the sixth. Notice that we can combine similar terms. Now notice that we can actually factor an x squared out of the numerator. And notice that what is left is a difference of 2 squares. Now, what I would like for you to do is to look at the example that is in the textbook. Look at all that work that you see right there, and look at how much work is left out of the problem. That's why it's important for you to work through the problems and make sure you understand them, because they often leave out many key algebra steps. So your aloha is important. Now, there's another way to do this derivative problem. What about distributing the 9 across the top and then write 2 separate fractions and reduce them? All of this is part of the rewrite process. Now, let's find our derivative and rewrite that, and we get that. Same thing as what you have here. Again, you would still need to factor out the 9 and factor your difference of 2 squares. Now, the really important thing, since this factors is at 3, 2, my x is 3, we're going to substitute 3, and we can see when x is 3, the derivative will be 0. So the value of the derivative at the given extrema is 0. Example 2. Find the critical numbers of f of x equals the absolute value of x. All right, we know that the absolute value of x looks like this. And I'm going to think about this from the left and the right. If you notice, from the left-hand side, that slope is -1, and from the right-hand side, that slope is +1. Look at that notation. The limit as x goes to 0 from the left on the first derivative. That slope is -1. This slope is 1. Those are not equal. So this is an interesting thing to notice. We're going to use the alternate form of the derivative. The alternate form says the limit as x goes to 0 of f of x minus f of 0 over x minus 0. Well, what we know is our function was absolute value of x minus evaluated at 0 gives us 0 over x minus 0. I'm going to take the limit as x goes to 0 from the left. From the left-hand side, remember that when the quantity inside the bars is negative, its absolute value is the opposite of itself. So that is going to give me negative x over x, which is -1. So the limit as x goes to 0 from the left is -1. Now let's look at the limit as x goes to 0 from the right. Okay, we're going to take our derivative from the right side of 0. The limit as x goes to 0 from the right of f of x minus f of 0 over x minus 0. Here is our f of x minus f of 0 over x minus 0. As we come to 0 from the right, the quantity inside the bars is not negative. Absolute value of something not negative is itself. This over x is 1. Notice the derivative from the left is not equal to the derivative from the right. So our derivative at 0 is undefined. And that's a really important thing. The function itself is continuous, but the derivative from the left side of it is not equal to the derivative from the right side of it. The x values at the extrema are called critical numbers. This is where the graph usually changes directions. Not always, but it is going to be where f prime of c is 0 or f prime of c is undefined. So we'll notice up here, I could write this function in a piecewise way. So f of x is negative x for x less than 0 and positive x for x greater than 0, and it's actually equal to 0 when x is 0, but the derivative does not exist when x is 0. The derivative from the left is -1. The derivative from the right is 1. It says to see the blue box on page 166. Let f be defined at c. If f prime at c is 0, or if f is not differentiable, then c is called a critical number. Here is a situation where f prime at c does not exist. Why? Because this is a sharp point. Here is where f prime at z is 0. We have a horizontal tangent. If f has a relative maximum or a relative minimum at x equals c, then c is a critical number of f. See page 167, a gray box, for steps in finding extrema, max or min, on a closed interval. To find extrema of continuous function f on a closed interval, use the following steps. First, find the critical numbers. In other words, find where f prime of x is 0 or undefined. Second, evaluate f at each critical number. So f of c, whatever place where this was 0 or undefined. 3, evaluate f at each endpoint. The least of these values is the minimum. The greatest is the maximum. Find the extrema of f of x equals 3x to the fourth minus 4x cubed on the interval from -1 to 2. So first of all, we're going to differentiate to find the x values of the critical points. So the derivative is nice and easy. F prime of x is 12x cubed minus 12x squared. Now our critical numbers are going to happen where the derivative is 0 or undefined. Since it's a polynomial function, it is continuous on the interval, so it's differentiable, and we will be able to find a place where f prime of x equals 0. Taking our derivative, setting it equal to 0, and doing the necessary algebra, we can factor a 12x squared out of here, and I get 12x squared equals to 0, or x minus 1 equals 0. My critical numbers are at x equals 0 and x equals 1. Now, there's a little more algebra you can do when it gets around to sketching this. You certainly can see that in the function, I can factor x cubed out, and my zeros are going to be of my function where x is 0 and where x is 4/3. Also, you might remember from pre-cal, this is a linear root. That means that we're going to pass right through 4/3, and my y values will go from positive to negative or negative to positive. But this is a multiple root. X is 0, and x cubed is going to make this behave like a cubic function as it passes through the root. So just some ideas of what it's going to look like. So we're going to now find the left and right endpoints of the function, and we're also going to evaluate f at 0 and f at 1. So f at -1, which is one of our endpoints, is substituted into the original function. It is 7. F at 2, which is the other endpoint of our closed interval, and I get 16. Now I need to evaluate f at my critical numbers. F at 0 is 0. F at 1 is substitute into the original function, and I get -1. So I can sketch the point -1, 7, 2, 16, 0, 0, and 1, -1. I can see that as we come through 0, I have a multiple root. It behaves like a cubic function. And here at somewhere it's going to turn around. In fact, I have a horizontal tangent when x is 0 and when x is 1. And then it's going to pass back through the x-axis at 4/3 and go up here. And you get an idea of it, and you can see that this is clearly going to be where my minimum is, and my maximum is going to be there, but we can't always base it on the graph. We have to base it on what we know how the math does. So my left endpoint is the point -1, 7. My critical number when x is 0, the point is 0, 0. My critical number when x is 1, the point is 1, -1, and my right endpoint 216. Clearly, lowest value, highest value. Absolute minimum, absolute maximum. Why? Because I also checked at the endpoints. Determine the critical points of f of x equals x to the fifth minus 5x to the fourth plus 5x to the third plus 2 on that interval from -3 to 3. So what are we going to do? First, again, we're going to find f prime of x, set it equal to 0, and solve it. This is a polynomial function. We know it is continuous, so we will not have a situation where the derivative is undefined. There's my first derivative, set it equal to 0, and solving it, I can factor out a 5x squared, and what remains can be factored. And so my critical numbers are 0, 1, and 3. Now we can look for absolute extrema. F at -3, substitute -3 in here, and we get a huge negative number, -781. I don't know its absolute minimum yet. F of 3 is -25, so I've got my two endpoint y values. My critical numbers, f at 0, substitute in, is 2. F at 1, substitute in, that's 3. And f at 3 is -25. So my lowest y value is -781. My highest y value is 3. So my absolute maximum is 3. That happens when x is 1. My absolute minimum is -781. Happens when x is -3. And you don't know enough yet about how to sketch the graph, but you can plot these points. And you can see we're going to have a horizontal tangent when x is 0, when x is 1, and down here when x is 3. And your 3.1 TPs are 3, 7, 15, and 19. See you in class.